So in the previous video, we were actually discussing about what are the basic classifications of the signal. We have discussed about the continuous time and discrete time signal. We have discussed about analog and digital signal and also about the deterministic and random signal. So in this video, we'll be discussing the other classifications of the signal. The first one is the periodic and aperiodic signal. So the basic meaning of a word period is something which repeats after some time, right? So similar to that, in case of periodic signal also, a signal which actually repeats after a specific time period or whose pattern will remain the same after a specific time period is what I call it as a periodic signal, okay? So in terms of equation, if I have to define it, I can define it as x of t that is equal to t plus t, which the capital T will actually define after a specific time period, okay? So one such example is the sine signal, which I can denote it as sine of 2 pi ft, which means, for example, if I am taking the time period as 0 to 2 seconds for one complete cycle, after the 2 seconds, the signal will actually be the same, which is in the 0th second, right? So that is what we call it as a periodic signal. An aperiodic signal is something that which does not repeat after a specific time period. For example, I can say my speed signal as a aperiodic signal because I'm not going to talk in the same speed or the same level of sound after the 10th second or the 11th second, right? So the speed signal and the ECG signal will be actually varying with respect to time, and the pulse signal also. When I want to talk about the comparison of the periodic and aperiodic signal, in terms of repetition, it repeats after a specific time period, and aperiodic signal does not repeat, okay? And talking about the period, it has fixed number of fixed periods actually exist, and in case of aperiodic, there is no actually fixed period. And one such example is sine wave, and for aperiodic signal, we can include the speed signal, okay? So talking about the even and odd signal. So even signal, any signal, if in case if it is shifted in terms of time, also if the signal remains the same even after time reversal is what I call it as the uh, even signal. So after time reversal, if the signal characteristics changes, then I can call it as an odd signal. So the condition for even signal will be x of t that is equal to x of minus t, which means even after time reversing the signal will remain the same, right? In case of odd signal, I can take the signal, for example, x of t is equal to sine t. In that case, if I'm time reversing the signal will not remain the same, okay? So in case of decomposition of any signal, we'll be able to decompose the signal into even and odd component, okay? So if I want only the even component of the signal, I can use the formula x e of t that is equal to x of t plus x of minus t divided by 2, and for odd component I can use the formula x of t minus x of minus t divided by 2. Okay, so next we are going to discuss on the topic of energy and power signal. So in case of an energy signal, for an finite total energy, E that is equal to integral minus infinitive to plus infinitive modulus of x of t the whole square into dt, which means for any signal which has finite energy, the average power of the signal will be zero. For example, I can say it as a pulse signal. But dealing with the power signal, for an finite average power, so power will be equal to limit t tends to infinitive 1 divided by 2 into t integral minus t to plus t modulus of x of t the whole square into dt. So, in case of a power signal, the energy will be infinite, and in case of the energy signal, the power value will be 0. Okay. So, total energy in case of the energy signal will be finite, and in case of the power, it will be infinite. And for the average power, the energy signal, it will be 0, and for the average power for a power signal will be finite. So example for energy signal will be your pulse signal, and the power signal will be the sinusoidal signal. So next we are going to discuss on the topic of real and complex signals. Okay. So when I actually call a signal as a real signal is that whenever it contains only a real number component, then I can define that signal as a real signal. For example, x of t is equal to phi into cos t has only real component in it. But if I want to discuss about the complex signal, it also has the imaginary part in it. For example, x of t that is equal to e to the power of j into t, I can decompose that e to the power of j into t as cos t plus j sin t by using the Euler's theorem. From this, we'll be able to see that it also has the real term and also has the imaginary term. Okay. Next, we are going to discuss on the signal which is causal, anti-causal and non-causal signal. So, when a signal exists only for the time period greater than or equal to 0, then such kind of signal is what we call it as the causal signal. Okay. So, present input will depend on the present output will depend on the present input signal. That is why we are dealing with t is greater than or equal to 0. But in case of the anti-causal signal, so it exists for a time period which is t less than 0, which means for the previous values alone. So for a non-causal signal, the signal will exist both in the positive and negative direction. Okay. So next one is the finite and infinite duration signal. So finite duration signal is something which occurs only for a specific time interval, and infinite duration signal is something that which exists for a huge amount of values or forever. Okay.